We're looking at AP Physics C, Electricity and Magnetism. We're specifically looking at the 2010 free response question, question 1. And here it is here. What we have is some set of linear charge in a circular format. So a charge plus Q is uniformly distributed over a quarter of a circle. So that right there is big. It's a quarter of a circle of radius r. Points A, B, and C are located as shown, with A and C located symmetrically relative to the x-axis. Whoa. What was that? We're expressing all algebraic answers in terms of given quantities and fundamental constants. And for the first part of this, we are ranking the magnitude of the electric potential at points A, B, and C from greatest to least, 1 being the greatest, and if 2 points have the same potential, we just label them the same. So the big thing to remember is when you're looking at a potential, it is a scalar quantity. Okay, so a potential, which is just V, it's a scalar. And since it's a scalar, we just add them up. And we know that for an electric potential due to some charges, that's just going to be KQ over R, some distance there away. In our case, that's the big R, because big R is what they gave us in this problem. So we know at point B, we're closer than we are at point A or C. That's just what we see in this diagram. So point B is going to have the smallest value of R, and a small number of the denominator means a larger outcome. So we're going to get B to be the number 1. And then A and C, they are symmetric, and they're both set up equally spaced away. So both A and C are going to be 2. Okay, and that's just, we're looking at scalar quantities, just how close are you to this, okay? If we look at the next part of this, part B, if we have some point P at the origin here of this xy plane, then to determine an expression for the electric potential at point P due to the charge Q, we've actually got something pretty straightforward here. There's actually 2 ways to do this. You could actually go solve for the electric field there and then go backwards by taking an integral. But the easier thing to do here is to recognize that a potential is just the KQ over R. And in our case here, we are trying to add up all of the little bits of Q. Well, if you're adding up all of the little bits of Q, and we could write that, if we wanted to write that in like a differential form, we could write it as dq. But if we're just adding up all the little bits of charge, and all the little bits of charge are the same distance away, then when we add them all up, we're just going to get the total charge at the distance away. So in the end, this is just going to be K times Q, which is the actual charge of that piece of the ring, divided by R, which is the R there. And we didn't need to do any integral here, simply because this is already set up so that we know the charge that is sitting there, and that if we were to integrate over all of it, we would just get the charge. And we can do that because this is a potential. You just add all the little bits together at the same distance. When you add all those little bits together, you just get Q. Now, this might be a little bit different if this wasn't a circular charge, if this was a line of charge. Now we have to start recognizing that the bits of charges are different distances. But in a nice circular case that we're looking at here, we don't need to do that. For part C, we have a positive point charge Q with mass M placed at point P, and then it's released from rest. So we go back to our diagram. We take a positive charge, we put it right here. It's initially at rest, and then we let it go. And because this is a positive and this is a positive, this is going to jolt away. And if we actually look at a little bit of symmetry, like we'll do later on, we'll see that it's going to move along the x-axis. And what we're just asking for is when this particle gets an infinite away, what is its final velocity. So the final velocity a very far distance away. And when they say very far, what they are talking about is they're talking about infinity. So anytime you see anybody say very far or very long, they're talking about infinite, okay? So to approach this problem, what we're actually doing here is we're looking at a conservation of energy. And what we're looking at is what initial potential do we have plus what initial kinetic do we have, and that has to equal the final potential plus the final kinetic. Now, what's nice about this is that since we started from rest, our initial velocity is 0, which means that the initial kinetic is 0 as well, so that goes away. The other thing that's really nice is we know by the way we've defined our potentials is if you are at an infinite distance away, your potential energy is 0. So what we can say here is that at a potential, or a final potential at infinity is going to be 0. So that goes away. So all we need to know is that the initial potential we have is equal to the final kinetic. If you are looking for a potential energy here, and that's what this is, it's a potential energy. Remember, a potential energy is very closely related to a potential, but a potential is just if an object was placed there. So if we think back to gravity, and we were talking about gravitational potentials back whenever we did mechanics, you know, I could take an object and place it above someone's head, and that object would have gravitational potential energy, mgh. And if I dropped it, it would hit them in the head. But even if I didn't have an object, I could still put one above your head. Like, there's the possibility 20 pound brick would just appear above your head, if you had an improbability drive, but there's nothing there. There's just the potential for something to be there. When you place the object there, it then has an energy. So if we wanted this electric potential energy, or the potential energy we get from this field that exists, well, we know the potential. The only thing we need to do is put an object in there. And for electrostatics, the object we put in is a charge. And then we know, based on what we did with kinetic energies all last year in mechanics, you know that kinetic energy is just 1/2 mv for speed or velocity squared. Okay, so we just need to set these two equal to each other, and we'll get a value here. So let's just run through and grab that. Q times V, well, what's the potential at the center of that ring? It was KQ over R. That's what we solved in part B. And even if you didn't get KQ over R in part B, use whatever you got there. There's nothing wrong with saying, hey, look, this is what this equation is. It's a charge times a potential. This is what I got for the potential. I'm using it. If that answer you got for the potential is wrong, but you use it anyways, you'll get a continuity point for that. They'll keep giving you points as you go forward. So we're going to get the charge we placed times KQ over R. Note, these Q's are different. This is the charge that's placed at point P. And then this here is the charge on the arc. Okay, so that's the arc there. Okay, so we've got QV, and that has to equal 1/2 mv squared. So now if we just want to go ahead and solve for velocity, we can do that. A little bit of algebra time. We're going to take this 2 and multiply it over, and we are going to then divide by the mass, and then we're going to take a square root. So when we move the 2 over, we're going to get 2QKQ, and then the denominator, we have our R, and when we divide it by that mass right here, divided by m, you have the mass. That equals the speed squared. If you need to get rid of a square, you're probably familiar with this, but you take the square root of both sides. So when we take the square root over here, that's going to get rid of that square root, and it's going to give us our answer for that one. Okay, so we get the square root of 2qkq over mr. And however you like to rearrange those, some people like to write 2kqq over mr. That's fine. It's multiplication. Any order you want to do it, it's cool. Okay? So that's how we can go about that. At this point, you have just done an AP Physics C problem, just about 2/3 of the way through, and we haven't touched calculus yet. At this point, we'd have earned out of the 15 points total 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 out of 15 points. And if you're earning 9 out of 15 points, you're doing a great job. Then you can be confident that you're going to score like a nice 4. Okay, assuming you did, reasonable on the multiple choice section. For part B, here's an easy 10th points going here. On the dot below representing point P, indicate the direction of the electric field at point P due to the charge. And what charge they're talking about is they're talking about charge Q, the total charge on that arc there. And if we go back to that arc, I mentioned before that there's a lot of symmetry here, and our particle is going to go to the right. The reason it's going to do this, and we can look down here for this, is if we take a small bit of the charge up here, it's going to give an electric field going this direction. If we take a little bit of the charge down here, it's going to create an electric field going like this. Now, these bits have the same amount of charge on them, so these lines are going to be equal, which means the vertical components are going to cancel each other out. So the E field in the y direction is going to be 0. Okay? What will not cancel each other out are the x components of these vectors. Both of these vectors are going to be going to the right, and therefore, if we kind of take a look at that triangle, we're going to have a cosine component. If there's our blue and then here's the maroon that we're going to keep, if we knew this angle, theta, well, the maroon here is just that blue line times the cosine of theta there. Okay, so we're looking for a cosine component, but all of the electric field is going to be acting to the right. So at this point, we can just say, whoosh, that's the electric field. It's acting to the right in the x direction. And that right there is a point. So you just went 10 out of 15 points without doing a drop of calculus. Okay, so you don't need a lot of calculus in order to do well on this test. Even though it is a calculus-based test and a calculus-based class, the AP Physics C, you don't need a lot of calculus in order to do well on it. You have good fundamentals of what's going on with electrostatics for a question like this, and if you do know the calculus, we can get a few more points out of this problem and kind of squeeze it through. Okay, so part E is where the calc starts coming in, and what we're asked to do is we're asked to derive an expression for the magnitude of the electric field at point P. Now, when they say derive an expression, they're really asking you to start from the very, very beginning. Okay, and what we mean by that is just like start up as high as you can for your base knowledge and work your way from there. So when I look at a problem like this, and we just drew this, but I know I've got a bit of charge here pointing down like this. I know I've got a bit of charge here pointing up like this, and that means that everything I care about is acting to the right. I really care about this E field in the x direction. And that E field in the x direction is the combination of all the little bits of charge in this arc. Now, the thing that's a little bit weird is that as you move through this arc, you're going to get different amounts of E field from each piece, because while the blue and red vectors there have some length, all of these vectors are going to have length, but that vector that's sitting right here, all of it is going to be pointed in the x direction. So that green dot, that green bit of charge on the x-axis is actually going to push in the x direction more than the charges on the end. And because of that, what we're trying to do to find that total the electric field in the x direction, is we need to add up the components to all of these charges. So the electric field at point P is this e to the x. So the magnitude of the electric field, which when they say magnitude, they're talking about an absolute value. If you don't put that, that's fine. But they really want you to say that this is in the x direction only, which we know. We solved that in part D. But this is really the addition of all of the little bits of charge pushing in the x direction. And when we start talking about little bits of charge, or little bits of anything for that matter, what we're really talking about is a differential component. We're talking about a tiny, infinitesimal little bit that is so small that it's been chopped into an infinite number of pieces. And if we wanted to add all of them back together, then you would just get the total thing back. So this electric field in the x direction, it's the addition of a bunch of pieces of the electric field in the x direction. And the way we write this is to say that we're adding a lot of things together. What we do is we write this integral, okay? It kind of looks like a big squiggly S, but it's an integral symbol. And what it represents is just the addition of many tiny little pieces. And we say that these tiny little pieces, we represent this mathematically with the term d, which means just a differential or a tiny little piece of whatever it is we're looking for. And in our case, it's the electric field in the x direction, okay? So if you're familiar with this idea of an integral, hopefully that's not surprising to you. Maybe if you're in Calc 1 or Calc AB, that's something that you're just seeing. And what we're really doing is we're just adding up. Remember, this just means adding up. And then these are small bits. And in this case, the small bits, what we have are the electric fields in the x direction. Okay? So how would we write this out fully in a mathematical format? Well, we know, and we're really going to focus on this right here now, because all these are going to end up equaling our answer. We know that if we added up all of the E fields in the x direction, well, we got these E fields by taking that cosine term for all these values. So if we added up all of the bits of the electric field itself from each of these infinitesimal pieces, but then we took the cosine of theta of all of those things, we'd get our electric field in the x direction, which that's what we're looking for. Now, that looks really weird. We've got this theta here and these electric field pieces. That's not exactly written in a nice way. Well, if we think about what the electric field pieces are, well, it's a tiny bit of charge is giving an electric field. And we know that just in general, an E field is KQ over R squared. So if you had a tiny bit of E field, that's given to us by a tiny bit of charge. So we can say that a tiny E field is given by K and then a tiny bit of charge, dQ, over R squared. So we're going to take this value and we're going to drop it up into there. So that we can rewrite this, we can say that, hey, our final answer here for the magnitude of the electric field, which is just the electric field in the x direction, is equal to this integral of K dQ over R squared cosine of theta. Now, one of the issues we run into as we're doing this is that we cannot actually just say, well, if you added up all of the little bits of charge, you'd get the whole charge here, okay? And that's true. You'd get the whole charge on the arc, but because you have an arc there, we actually need to integrate with respect to a distance, okay? So what we need to do is we need to take that dq term and we need to somehow relate it to a distance. Well, we can do that. And the way we're going to do it is thinking back to that charge that's sitting in this arc. This arc here has some arc length going from here to here. And it's got this arc length just like that. We'll call this arc length L for length, but you could call it S. A lot of people do call it S. So this is just some length here, L or S. It's really up to you. It's whatever you'd like to use in your book. But because this charge is spread out uniformly over this length, we can say that this arc has a charge density. It has some charge per unit length. And we can write this charge density as saying lambda, this is our charge density, it's equal to the charge that we have, that plus Q, divided by some length. Well, we could rewrite that just by saying that Q equals lambda L. I just moved that L over. Now what this means is that if we have a tiny bit of charge that we've taken a look at, some infinitesimal piece of the charge, something like dq, then what we've done is we've taken the charge density, which is a constant, it is something over that length, and we've taken a tiny sliver of the length, dl. Well, that's all and good, but how do you get the length of an arc? How do you get an arc length there? Or how do you get a tiny piece of the arc length? And this is where you have to think back to something that we're pretty familiar with, or we should be, from geometry. You know the circumference of a circle, or the distance around the perimeter, the distance around the edge, the length around the edge? That's equal to 2 pi r. But why is it 2 pi r? Well, in general, an arc length, which we can say S, or as I've said here is L, it's equal to an angle times some distance you are away. You know, what is the radius of that circle you're creating? So if I wanted a tiny piece of L, dl, well, that would be equal to a tiny bit of the angle times how far are you away, what is the radius of that circle. So we're going to take this value and dump it back in for dl here. And then we're going to take all of this and put it down for dq. And that seems like a really weird thing, but we're going to see that more and more as we do these type of problems. This is super important here, okay? This is something that doesn't pop up on any equation sheet. It's just something that you need to know. It's something that you need to be thinking about, and you need to be thinking about these distributions of charges, because that's where we need the calculus. So if we come back down here and we write this out, we can say, hey, look, this equals the integral of k, and then we've got that we're bringing down lambda, and then our dl is actually d theta r d theta. I'm going to write it as r d theta over r squared cosine of theta. Okay? Now what we also need to do here is we need to ask ourselves, whenever we're looking at this, what is stuff that we can pull out of this integral, and what needs to be left in the integral as well. Well, we can pull out of the integral any constants we have. K, electric constant, constant. Lambda, constant. These R values are the distances to point P. It's just the radius of the circle. So these are actually constants, and if we wanted to, we could actually cancel one of these R's out. We're not going to at the moment. We're going to see why later on, a little bit of insight. But we can pull all of these outside of the integrand. So we can say that this is now equal to k lambda r over r squared times the integral, and I'm going to write this as cosine of theta d theta, because that's probably more like how you're going to see it in your math classes. Now, one of the things we need to recognize is that we need boundary conditions on our integral. We need to say, hey, look, we're integrating along this arc, the theta, you know, what is this theta here? But what are these angles? Well, if we go all the way back up to the beginning of this problem, it said it was a quarter circle of radius r. And there's a lot of way to write the quarter circles, but if we kind of take a look at it, we've gone up pi over 4, and then we've gone down pi over 4. So one way we can write this, if we go all the way back, is that our bounds, where we're going to and where we're going from, can be written as pi over 4, because we're going one way. And then if you go the opposite direction, those are actually negative angles. And these need to be angles that we're using here, because that's what we're integrating with respect to. We're integrating with respect to angles. So negative pi over 4. Okay? If you were able to get to this point and you know nothing about integrating, but you're just like, I set this up, okay? Or even if you got, you know, maybe somewhere like around here somewhere, and you're like, I don't know. You just picked up an extra like 2 points. So you just went 12 for 15 on this question. Congratulations, like you're getting a 5. But let's say you did want to solve this integrand, or you had some extra time at the end of the test, you're like, I'll go back and solve it. Well, the integral of cosine d theta, that's actually an integral sitting on your equation sheet. It is equal to sine. So what we can do is we can carry all of our constants over, k lambda r over r squared times the quantity of sine of theta, pi over 4, negative pi over 4. What this pi over 4 and this negative pi over 4 represent, is, like I said, these are our bounds. But what we have to do here is, and the way they traditionally teach it in math, is basically a top minus the bottom. Okay? So you take your top value, in our case pi over 4, and we'll sub it in to the sine of theta. So we're going to get the sine of pi over 4. And then we're going to subtract, and then we're going to take our bottom value and plug it in for theta. So we're going to have sine of negative pi over 4. Nice thing about sine function, anytime you get a negative on the inside, you can bump it out, turning that positive. And naturally, coming down with us are all of our constants, which are k lambda r over r squared. Remember, these r's, they've labeled them as big R in the problem. I've just left them as r's. And then we just need to put all this stuff together. If we do that, sine of pi over 4 is square root of 2 over 2 plus square root of 2 over 2. That just gives us square root of 2. And we can actually say that our electric field in the x direction here is equal to square root of 2 k lambda r over r squared. If we wanted to, we can say, hey, look, these r's go, one of the r's go away. Okay? What we're actually going to do, and this is what they do in the solution, because this is also a valid thing to say if these r's go back, is you actually know in this problem what lambda is. Okay? So while this is a great solution right here, you can clean it up just a little bit more. We actually know that lambda in this problem, it's equal to that total charge, Q, over that length. And we know that if this is a quarter circle, the length is pi over 2, that's the angle, times r, times that distance. So if we plug this back in for lambda, then this becomes a little bit cleaner. We end up getting that our final solution, which is the x direction, is going to equal, well, if we write this out, square root of 2k, and then we're going to have a q over pi over 2 times, well, with an r in the denominator, times r. These r's are going to cancel. This 2 in the denominator is going to come up to the numerator, and then that means this pi in the denominator can sit with the r squared value. So the way we can write this, finally, it seems like it's taking forever, is 2 square root of 2k times the total charge over pi r squared. Okay? really, we were done all the way up here. But if you're just looking for this to be written in terms of, and what did they ask for? In terms of the given quantities in fundamental constants, then they're asking for you to put it back in terms of Q, which this is done here. Okay? So you may have gotten a point if you left it up here like this, but by using this right here, we were able to get it back and finish up the problem. And if you did that integral and you worked your way through it, you just got 15 points. But if you didn't, if you stopped, you know, all the way up here, you got 12, which means that all of this work was like 3 points. That's a lot of work for 3 points, considering that when we look at the entire problem, you know, we got 10 points or 12 points for doing all of this. Okay, so we got a lot more points for doing easy stuff than we did for doing that calculus. So my recommendation is, hey, look, if you get through a problem and you find the calculus, see if you can set up the integral and then ditch it, because actually going through that math is going to take you some time, and you may mess something up. It's also something that, you know, if you're using a value from previously in that integral, hopefully you use the right value, but there's always a chance that you set something up poorly in the beginning, and when you go and carry it forward, now you've given yourself a nearly impossible integral to do. So don't waste your time with the integral. Just set it up, run away from it, go do some more stuff on later problems, come back when you have time and see if you can solve it out. Okay? But that right there was the 2010 Electricity and Magnetism question 1. You're looking at a arc of charge and looking for potentials and electric fields for it. With that, we're finished.